All right, let's move into some three-dimensional figures with this lesson. We have three-dimensional figures all around us all the time, so we'll take our knowledge about two-dimensional figures and increase it to 3 dimensions in this section. First term is a prism. Prism is defined as a solid with 2 congruent faces, where all the other faces are parallelograms. So most of the time, those parallelograms are actually going to be rectangles, but sometimes a prism can be tilted. It's called an oblique prism, in which case the sides are parallelograms without right angles. And so just to keep it general, parallelograms, but most of the time they're rectangles. So you see an example here with these 2 prisms. They have top and bottom faces that are congruent to each other, and they're surrounded by rectangles. In the second one, we have a pentagon and a pentagon opposite, and then rectangles surrounding it. So both of these qualify as prisms. So why are they called right prisms? You have a conjecture, write it down, and you can check it. If you look at all of these are, when it's standing straight up, it's forming right angles with the base. And so that's where we define it as a right prism. This term lateral faces means around the side of it. So when the side faces, those lateral faces meet the base at a right angle, it's called a right prism, as opposed to an oblique prism where it is tilted. So if you slice the prism with a horizontal plane, just think about slicing it straight across the middle, what would be true about the cross section? You could take this hexagonal prism to try to understand it, but look at the hexagon on the inside compared to the ones on the outside. And it's going to be congruent to those bases as long as you slice it parallel. If you slice it vertically, what we're going to end up with is a rectangle that's the same height as the prism. It'll always be a rectangle if you slice down vertically. All right, so those 2 cross sections, it depends on which way you cut it as to which kind of figure you get. All right, so if a cylinder is very similar to a prism, except that lateral surface is not rectangles, it is a continuous smooth surface. Most commonly, we have a right circular cylinder. That's typically what you see like in cans. Those are the most common version of it. For a right circular cylinder, what are the 2 measurements that control its size? Well, this thing will change if I change the radius of the circle, because then the top and the bottom will change. Or if I increase or decrease the height, that will make it a taller or shorter cylinder. So those are the 2 things, the radius of the bases and the height. So what kind of figure wraps around it laterally? If you were to cut this vertically, like to picture this being a paper towel tube or something like that, if I cut it vertically and unroll it, what I'm going to get is a rectangle. And so the rectangle is going to have a height that's the same height as the cylinder, but then the length is going to be whatever the length of the circle was, otherwise known as circumference. So the length is the circumference, and the width will be the height of the cylinder. All right, so that's called the lateral surface of the cylinder going around the side. So what 2-dimensional figure, when rotated about one of its sides, would produce a right circular cylinder? Draw this cylinder to illustrate. So I'm just going to think about a rotation now. So if I were to start in the center of this thing and go to the edge with my radius, in order to make this circular, what I would need is for that radius to also duplicate on the bottom of the figure. And you can see what shape I have now. If I started with a rectangle and I rotate that rectangle, picture a central axis right here. Rotate around that central axis, it's going to sweep out a cylinder. It's going to pass through a circular path, and it's going to make a cylinder. So what if I start with a rectangle and I rotate it in the center, I will end up with a cylinder. All right, pyramids. Pyramids are similar to prisms, except that they only have one face instead of 2 parallel faces, and then they have all of these surrounding lateral faces as well. So what happens is that one base has a series of triangles emanating from those edges, and they end up meeting at a point. They taper to a point. So they meet at a common vertex. The base could be a square, could be a pentagon, could be any polygon really. And then however many sides there are in that base polygon will determine how many triangles come up from the bottom and meet at the top. So if this is a square pyramid, that means that it starts with a square on the bottom and there are 4 sides that meet at the top. So explain why the horizontal cross sections of these pyramids would not be congruent. Well, the figure is going to change size as it gets closer, because as we move up the pyramid, it's tapering to a point. And so, yes, they are all similar to each other, but they're going to keep getting smaller as you get closer to the top. So if I slice this thing, I will always get a pentagon. that pentagon is going to get smaller and smaller as it goes up. So under what conditions would the triangular sides have to all be congruent to each other? So if that base starts out equal, if it's a regular polygon, then all of those triangles coming from it would have the same size base, and they would all be meeting at the same point, and so they'd all be congruent to each other. But as soon as you make this base irregular, now the triangles have to be different too in order to meet at a point. All right, cone. Cone is a lot like a pyramid in that it comes to a point, but it's also like a cylinder in that it starts off as a circle and has a smooth surface. So there's a couple of different properties that converge to make a cone. So similar to a cylinder, a cone can be produced by rotating a two-dimensional figure. So you can sort of see it started here already with this axis drawn in here, right? If I take this and attach it to a radius so that I can rotate, if I rotate this around, the figure that I'm rotating is this triangle. Okay, this right triangle, as it rotates around, is going to create a cone as it moves through. Right? So that if I didn't have a right triangle, then I wouldn't have a right cone. I would end up with an oblique cone, but the right triangle will create this. All right, so last thing, describe the cross sections of the cone shown below. So I want you to try all four of these, see if you can come up with an answer for all four. Looking at the cross section on the inside, trying to name what you see. This last one is a vertical cross section, just so you can picture what's happening there. All right, first one, I think everybody probably found a circle. I'm guessing everybody saw a triangle on the last one. This one here is an algebra concept. What I'm doing there is I'm slicing off a side of the cone, vertically, slicing off the side of the cone. And so what we end up making there is called a parabola. And that's the symmetrical U shape that you see on the side. And if you said oval for this one, you're on the right track. The technical term is ellipse. So that's if you sliced a little bit off horizontal, going through two parts of the lateral surface, but going on an angle, you create an ellipse. So all of these are called conic sections. All of these things are what you see when you slice a cone in various ways.